Hi, so we're back with describing motion with graphs, but this time we'll be talking about acceleration versus time graphs or AT graphs. We have already discussed about PT graphs or position time graphs and velocity time graphs versus or velocity time graphs. Now for AT graphs, our x-axis is still the time, but for our y-axis, now we have values for the acceleration. Now, this graph tells us, or the area under the graph in an AT graph gives us the quantity known as the change in velocity of the object. Now, with regards to the slope of the graph in an AT graph, there's a quantity that can also be extracted from it, which is known as jerk. So jerk is the rate of change of acceleration, meaning it's how acceleration has changed throughout the motion of an object. For an acceleration graph, still the slope can be calculated with the use of the slope equation, where slope is equal to the rise over run. Now, since our y-axis is now acceleration, so the rise of our graph is with respect to acceleration already, which gives us a2 minus a1, or the change in acceleration, divided by our run, which is time. So we have t2 minus t1. And this a2 minus a1 is your change in acceleration, and t2 minus t1 is change in time, as what you can see there in the diagram. Now this slope, this graph here, the slope of that graph represents the jerk, which is the rate of change of acceleration. Therefore, if the slope is also the jerk, then jerk will be equal to change in acceleration over change in time. Now, what about the area? So we talked about the slope, and the slope can give us gives us the quantity known as jerk. But for the area under the acceleration graph, which is this one, the area here, it represents the change in velocity. Not velocity, not initial, not final velocity, but the change in the velocity of the object. So in other words, the area under the acceleration graph for a certain time interval is equal to the change in velocity during this time interval. So the area is equal to the change in velocity. So let's take this for example. We are to solve for the area in this graph. Now, since it's a rectangle, so the area of rectangle is equal to base times height. Now, the base is, we have here the base, which is 9 seconds, times the height, which is 4 meters per second squared, because that's acceleration. So the unit is meters per second squared. Cancelled. We're now left with meters per second, and 9 times 4 is 36. Therefore, the change in velocity is 36 meters per second. So the change in velocity between that time interval from 0 to 9 seconds is 36 meters per second. So let's have another example. A confident race car driver is cruising at a constant velocity of 20 meters per second. Meaning, by the start of our observation period, the driver is already moving at 20 meters per second. As she nears the finish line, the race car driver starts to accelerate. The graph shown below gives the acceleration of the race car as it starts to speed up. Assume the race car had a velocity of 20 meters per second at time 0 seconds. Meaning, by the time that we started with our observation, the car is already moving at 20 meters per second. So what is asked for this one is to solve for the velocity of the car after 8 seconds, which is shown in this graph. Now, how can we solve for the velocity if our initial velocity is 20 meters per second? Out of this graph, what we can solve for is the change in velocity, right? Because the area under this graph is equal to the change in velocity. So area of, since that's triangles, the area of the triangle. And the area of a triangle is equal to 1/2 base times height. So what's the base? Base is the time, which is 8 seconds. And the height, here you have 6 meters per second squared. So we cancel this, and we're left with 1/2 times 8, that's 4. 4 times 6, that's 24 meters per second. So meaning the change in velocity is 24 meters per second. Now remember that change in velocity is equal to v plus vi. Not plus, minus. V minus Vi. To solve for V, then V will be equal to change in velocity plus the initial velocity. So the change in velocity is 24 meters per second plus 20 meters per second. This one, given by this one. And our answer will be 44 meters per second. So this is our final answer. So the velocity of the race car after 8 seconds will be 44 meters per second. Again, the area here does not tell us the initial nor the final velocity, but it tells us by how much did the velocity change with the acceleration that was present in the motion of the object. Another example, a sailboat is sailing in a straight line with a velocity of 10 meters per second. Then, at time 0, a stiff wind blows, causing the sailboat to accelerate as seen in the diagram. So what is the velocity of the sailboat after the wind has blown for 9 seconds? So we have here the entire time for observation is 9 seconds. So what is the velocity? We now know, or we know from the problem, that we will start with a velocity of 10 meters per second, as stated in the first statement, that the sailboat is sailing at a straight line with a velocity of 10 meters per second. So what we need to do, since we are to solve for the velocity, or the final velocity, we will also do what we did in the earlier problem. But since we have changing slopes here, then we can divide the graph into different shapes. So we have here a rectangle and 2 triangles. So we just need to add all of the areas here. So let's take the first one, this one. So the change in velocity there is base times height, since that's the area. Now what's the base? We have here from 0 to 3, so that's 3 seconds. The height will be 4 meters per second squared. Cancel that out, and you're left with 12 meters per second. Now this one, the change in velocity in 3 seconds and 3 seconds to 7 seconds. And since that's a triangle, then that's equal to 1/2 pH. So 1/2, the base is from 3 seconds to 7 seconds, and that is 4, because 7 minus 3 is 4. Times the height is still 4 meters per second squared. So you're going to cancel that out. Then 1/2 times 4, that's 2 times 4, that's 8 meters per second. Now for the last one, the last triangle here, still it's 1/2 BH. Now 1/2, the base is still, you have here the base, now but just it's 2 seconds. Now the height of this triangle, if we look at it, it's already in the negative axis of the y, which is acceleration. Therefore, we should also input negative 2 meters per second squared. Thus, it's in negative, as you can see here. It's negative 2. So that will give us 1 half times 2 is 1 times negative 2. Then that is negative 2 meters per second squared. So those are our changes in velocity. But we still need to add all of those up. So to add all of those up, we have the change in velocity. We have 8 meters per second. We have 12 meters per second. And we have negative 2 meters per second. Now, the initial velocity is 10 meters per second. You need to solve for the total of this one, the total area, and then we will get, how much is that? That's 18 meters per second. It's not working. There, 18 meters per second. Because 8 plus 12 is 20 plus negative 2, then that's 18 meters per second. So this is the change in velocity, the total change in velocity. So the change in velocity is equal to Vf, or the V final, minus Vi. To solve for this one, then Vf or V final is change in velocity plus initial velocity. And the initial velocity is 10 meters per second plus 18 meters per second. So our answer will be 28 meters per second. Oops, 28 meters per second. So that's how we can use acceleration versus time graphs. Again, the area the area below the acceleration time graphs is equivalent to the change in velocity, not initial, not final, but the change from initial to final. What else? The slope of the acceleration time graph tells us the rate of change in acceleration, which is jerk. So that's it for this video. Thank you very much for listening.